Hey everyone, Mr. Hauk here. In today's video, we're going to learn about multiplying matrices. When multiplying matrices, there are two different kinds of matrix multiplication, multiplying a matrix by a scalar and multiplying a matrix by another matrix. We're going to begin with multiplying a matrix by a scalar. Now, when multiplying a matrix by a scalar, it's actually pretty simple. We're going to multiply each element of the matrix by that scalar to create a new matrix, and this is essentially just the distributive property. So let's see it with this first example. For the given matrix A, we want to calculate 2A. So here's our matrix A, and essentially all we're going to do is take 2 and distribute it to all the elements of matrix A. This is going to give us, well, if we do 2 times 4, this would be 8. 2 times 0 would be 0. 2 times 1 would be 2. And 2 times negative 9 would be negative 18. And it really is as simple as that. So once again, we're just taking our matrix, multiplying by the different elements in that matrix. We're taking the scalar, multiplying by the different elements in that matrix, and it creates a new matrix of the same dimensions. So let's try a couple practice problems here. In this first practice problem, given matrix A, we want to calculate negative 3A. Well, once again, let's just take this negative 3 and let's distribute it to every single element in this matrix A. Now, it's a lot of tedious multiplication, but at least it's pretty easy multiplication. So negative 3 times negative 4 is 12. Not negative 12. What are you doing, Mr. Hauk? Positive 12. Negative 3 times 1 is negative 3. Negative 3 times negative 1 is positive 3. Negative 3 times 3 is negative 9. Negative 3 times 7 is negative 21. Negative 3 times 0 is 0. Then we get 9. We get 3. And we get 24. So once again, slightly tedious, but a relatively simple process. Let's try a couple problems that involve multiplying matrices by scalars, but maybe have a little more critical thinking going on behind the scenes here. So in this next example problem, we want to find the value of k if k times this 2 by 2 matrix on the left will give us this 2 by 2 matrix on the right. Well, let's think about this here. Let's go ahead and distribute k to all the elements in this matrix. This would give us the matrix 2k, 3k, 5k, 6k, still equal to 6, 9, 15, and 18. Now, since the matrix on the left is equal to the matrix on the right, that means the first row, first column element on the left is going to have to be equal to the element in the first row, first column of the right matrix. So, setting up an equation, 2k equals 6, and dividing both sides by 2, this will lead to k equals 3. And it's not hard to double check the other ones here. If I plugged in a 3 for the k, well, 3 times 2 would give me 6. 3 times 3 would give me 9. 3 times 5 would give me 15. And 3 times 6 would give me 18. So we can verify that k is, in fact, positive 3. In our next example, we want to find the values of x and y given 2 times this 2 by 1 matrix, x2, minus the 2 by 1 matrix 6y equals the 2 by 1 matrix 5-3. Well, let's go ahead and distribute the 2 here. So this is going to give us the matrix 2x 4 minus this matrix 6y equals 5-3. Notice that since this is a 2 by 1, this is a 2 by 1, that we can subtract them. They have the same dimension. This would give us 2x minus 6, 4 minus y, equals 5-3. And very similar to the previous problem, we have a 2 by 1 matrix on the left equal to a 2 by 1 matrix on the right, which means that this element, 2x minus 6, is going to be equal to the element 5. Let's go ahead and set up an equation here. So 2x minus 6 equals 5. And similarly, 4 minus y should equal 3. Set up a different equation. And now we just need to simply solve these equations. On the left side, we get 2x equals 11, which tells us that x equals 11 over 2. On the right side, we're going to get that negative y equals negative 1, which tells us that y equals positive 1. Okay, so in summary, multiplying a matrix by a scalar, very simple process. It's just the distributive property where we take that scalar and we multiply it by every element in that matrix. Now let's talk about multiplying a matrix by another matrix. And this actually turns out to be a little bit more complicated. In order for, given two matrices A and B, in order for their product AB to exist, the number of columns of matrix A must equal the number of rows of matrix B. If matrix A has dimensions m by n and matrix B has dimensions n by p, then the product AB will have dimensions m by p. Or, to kind of see this a little more clearly, again, let's say that matrix A has dimensions m by n, and we're multiplying it by matrix B, which has dimensions n by p. Imagine that these two middle pieces would cancel each other out almost in a sense, and the new matrix will have dimensions m by p, these pieces on the outside. Okay, and we'll see this in action as we work through these couple example problems. So we're going to investigate multiplying matrices by other matrices using a very gradual approach to multiplying. First, we're going to take matrix A and B to be pretty small dimension matrices. A is going to end up being a 1 by 3 matrix. B is going to end up being a 3 by 1 matrix. And if we think about what the dimensions of the product should look like, when everything is said and done, if we're multiplying a 1 by 3 times a 3 by 1, well, again, imagine these little middle pieces canceled. We can expect that our matrix is going to be a 1 by 1 matrix. So it's really just going to be a matrix with one element in it. And let's see how that gets generated here. Okay. So in order to do matrix multiplication, watch the pattern that we end up developing here. It's almost like we're going to take all of row 1, multiply it to all of column 1 in the next matrix, and we're going to be adding those products together. So we're going to be taking, for example, 7 times 4 plus negative 3 times negative 2 plus 5 times negative 9, and that's going to give us one element in the new matrix. In writing, let's go ahead and write this down exactly what it would look like. So AB, the product AB, would look like this. We would have, again, 7 times 4 plus negative 3 times negative 2 plus 5 times negative 9. And notice it might be hard to see right now, but this is actually one big element, because once we simplify this expression, we're just going to have one number, and it's going to be a 1 by 1 matrix. So let's go ahead and simplify here. 7 times 4 is 28. Negative 3 times negative 2 is going to be plus 6. 5 times negative 9 will be minus 45. Continuing to simplify, 28 plus 6 minus 45 going to give us negative 11. And negative 11, this represents a matrix, a 1 by 1 matrix, one row, one column, exactly as we expected it to be. Okay? So let's see if we can follow that same pattern with a different product. So now we want to find the product C times D. In this example, C again, just like A in the previous problem, is going to be a 1 by 3. But now we're going to multiply it, instead of by a 3 by 1, we're going to multiply it by a 3 by 2. So let's go ahead and get an idea of what the answer is going to look like, what the product will look like. Well, if we're taking a 1 by 3 times a 3 by 2, again, imagine that those little pieces would cancel in a way, and the product, the result, should end up being a 1 by 2 matrix. Okay, so we know that our product should have one row but two columns, so two entries total, two elements total here. Okay, so let's get an idea of what this is going to look like before we actually go through and write out the process. Very similar to the previous example, we're going to be taking row 1 times column 1, so we're going to be taking like the 5 times 2 plus 1 times -6 plus -7 times 8, and that's going to make our first row, first column element. But then we have to do the same thing with the second row, or the second column here, rather, in matrix D. So we're going to take 5 times 5 plus 1 times 7 plus -7 times 2, and that's going to make the second element, the row 1, column 2 element. Okay, so let's put this in writing here. And I might have to write a little small here for space sake. So the product C times F is going to be, so once again, we're going to be taking this whole row from C, multiplying and adding with this whole column from D. We're going to get 5 times 2 plus 1 times -6 plus -7 times 8. That's going to make our first row, first column entry. Let's leave a little space between entries, between elements. And now we do the same thing. Take this whole row and do the same thing with this second column. So now 5 times 5. Not a 5 there. There we go. Plus 5 times 7. Plus, sorry, not 5 times 7. What are you doing, Mr. Huck? 1 times 7. So again, 5 times 5, that's that first part there. Then 1 times 7. Plus, lastly, -7 times 2. There we go. And we can already see we're going to get a 1 by 2 matrix. One row, two columns. Let's go ahead and simplify these pieces here. So 5 times 2, that's going to be 10, -6, -56. Leave a space between the next element. And then 25 plus 7 minus 14. Continuing to simplify, the 10 minus 6 minus 56 is going to give us a -52. And the 25 plus 7 minus 14 is going to give us a +18. And just as expected, notice this is a 1 by 2 matrix, one row, two columns, and everything looks good. All right. Let's try one last example. Again, it's going to get slightly more complicated, a little bit more math involved here. Notice here that in this last example on this page, we're going to be finding the product E times F, where E is a 2 by 3 matrix and F is a 3 by 2 matrix. Okay, so let's see what we can expect our solution to look like. If we're taking a 2 by 3 times a 3 by 2, let's go ahead and eliminate those little middle pieces there. We expect our answer to be a 2 by 2 matrix. All right, so let's talk about the strategy here again. For the first row, first column element, we're going to have, go back, Mr. Houck, there we go. The first row with the first column. Then we're going to take the first row with the second column. Then starting when we talk about the second row on our solution, we'll have the second row worked with the first column, and then the second row worked with the second column. So with all of that worked out, let's see what it ends up looking like. So the product, E times F, would look like this. So EF, we're going to have, again, we're going to take everything from row 1 with everything from column 1. So we're going to have 7 times 6 plus -2 times 3 plus 4 times 1. So again, 7 with 6 plus -2 with 3 plus 4 times 1. Then for the next entry for row 1, column 2, we're going to do everything from row 1 here, but now with column 2 here. So we're going to do 7 times negative 1 plus negative 2 times 5 plus 4 times 2. Now, moving to our next row, we're going to take all of the second row, 10, 11, 3, multiplied and added with all of the first column, 6, 3, and 1. That's going to get us a 10 times 6 plus 11 times 3 plus 3 times 1. And to finish off the process, everything from the second row with everything from the second column, that's going to give us 10 times negative 1 plus 11 times 5 plus 3 times 2. Now, just to save us a little bit of calculation here, I'm not going to go through all the intermediate steps. Let's do a little bit of mental math here. So we're going to have 42 minus 6 plus 4. So let's see, 42 minus 6, that's going to be 36. 36 plus 4 would give us 40. So row 1, column 1 will be a 40. Negative 7 minus 10 plus 8. So let's see, negative 17 plus 8, that's going to be a negative 9. So row 1, column 2 will have a negative 9. Then down here, 60 plus 33 plus 3, that's going to be 93 plus 3, 96. So row 2, column 1, 96. And then here, negative 10, 55, and 6. Let's see, that's going to be 45. 45 plus 6, that'd be 51. Okay, and just as expected, we can see that our solution is a 2 by 2 matrix, and we're good to go. Now, in general, you see our equation right down here at the bottom, and notice that in general, this is the formula for a 2 by 2 matrix multiplied by a 2 by 2 matrix, but the pattern is consistent no matter the dimensions you're multiplying by, as long as the dimensions can be multiplied by. Okay, and again, in order for matrices to be multiplied, the columns of the first matrix must be the same as the rows of the second matrix. So for this next part, we're going to talk about properties of matrix operations. So we know that for the real numbers, for operations on the real numbers, addition and multiplication are both commutative and associative. But what about for matrices? Is matrix addition commutative and associative? And is matrix multiplication commutative and associative? Well, we're going to investigate this using matrices A, B, and C below to see if these properties hold for matrix addition and matrix multiplication. Now, to make the work a little easier on us, we're going to go to Desmos to do all the heavy lifting. So I'm going to show you how we would do this, but let's hop over to Desmos. This is desmos.com/matrix. And the first thing we want to do is we want to store matrix A, B, and C. So I'm going to click on New Matrix. Over on the notes, matrix A is a 2 by 2 matrix, and it has elements -1, 2, 3, and 0. Matrix B is also a 2 by 2 matrix. So let's click New Matrix. Matrix B has elements 4, 0, -2, -3. Let's click New Matrix once more. Let's get Matrix C in here. This has elements -2, -3, 4, and 2. So this is going to help us a lot with our calculations and time saving. Now that we have A, B, and C stored, we don't need to keep writing these matrices out. Okay? So the first thing that we want to check, if we go over to our notes, is commutative, or does commutativity apply to matrix addition? So basically, we want to check, is A plus B equal to B plus A? Well, let's come over here to Desmos, and we'll just type in A plus B. Notice A plus B is a 2 by 2 matrix. It has elements 3, 2, 1, negative 3. And we want to see if that's the same as b plus a. Well, putting in b plus a, we also get the same matrix, 3, 2, 1, negative 3. So this, at least this example, shows that matrix addition is in fact commutative. Commutative meaning that we can add in any order that we want. So as long as these two matrices can be added together, it doesn't matter if we do matrix A plus B or matrix B plus A, they will be the same. So commutativity holds for matrix addition. Let's see if commutativity, however, holds for matrix multiplication. So we're going to test something, we're going to test the same thing. We want to test, okay, well, is A times B equal to B times A? Well, let's check. There we go. So let's try A times B first. A times B gives us the matrix with elements negative 8, negative 6, 12, and 0. And if I try B times A, notice I get something different. I get matrix with elements negative 4, 8, negative 7, negative 4. So we've already shown that matrix multiplication through this example is not commutative because multiplying in the order A times B did not get us the same result as multiplying in the order B times A. So here we can see that matrix addition is commutative, and we showed this through Desmos. And we also showed that matrix multiplication is not commutative. Okay, now let's try associativity. So first, for the associative property, it's saying that if we take A plus B plus C, that'll be the same as A plus B plus C. And remember, these parentheses mean that's what you do first. So is adding A and B first, then adding C afterwards, going to be the same as adding B and C first, then adding A with it? Let's go ahead and check. Oh, wrong screen. All right. So again, back to Desmos. And having saved A, B, and C in Desmos, again, is saving us a lot of time. So we're going to check A plus B, then plus C. Notice we get 1, negative 1, 5, negative 1. And now let's check A plus, and then parentheses, B plus C. And notice that we get the exact same matrix, 1, negative 1, 5, negative 1. So this is strongly suggesting that matrix addition is going to be associative. And now let's try matrix multiplication. So can we multiply in that sense? Can we do A times B, then that product times C, and would that give us the same result as multiplying A times the product BC? I keep going to that other page. All right, well, let's try it out. So we'll do AB times C, then we'll try A times BC, and notice that we get the exact same matrices, negative 8, 12, negative 24, negative 36. Again, strongly suggesting that matrix multiplication is associative. And it turns out, and we'll give proof for it later if we have time in the course, but it turns out that matrix addition is associative and matrix multiplication is also associative. So to kind of wrap up the idea here, almost all these properties, just like they work for real numbers, they almost all work for matrix operations as well. But commutativity does not work for matrix multiplication. This is the big one that we need to remember. We cannot multiply matrices in any order. The order is very specific and very important for matrix multiplication. However, commutativity does apply for matrix addition. Associativity applies for both matrix addition and matrix multiplication.